Okay, so hi everyone. So my name's Jerry. I'm from the University of Montreal in Mila. I didn't really note our annotations, but like our institutions here. But so today I'm just going to kind of briefly present this short paper, this paper we had at iClear 2025 this year. So this was joint work between with Hao from the Western University of Canada, and mainly with Huang. So he's also at the University of Montreal. So just to give a brief idea, this is about like an efficient attention. So maybe not all of you are familiar, but I'll kind of go with into like the basics like very quickly. So to start off, I think we're all pretty familiar with like transformers because we use them quite often nowadays with our just in basically any settings. Like it used to be for language, but now it's kind of moved on to like CV, like computer vision, audio, like multimodal language like models all the time. If you're familiar with like the previous research intention, one of the initial concerns has always been that the scaling of attention with respect to the sequence length is quadratic. So this can lead to some problems when it comes to like scaling to like really long sequences. So the reason why this is the case is because of the softmax, right? So you have like all your keys and queries, which is like every token in your sequence gets projected into one of them. And then you have to compute a lot of these dot products at the same time. So this is kind of has become like the bottleneck with like what everyone like that people usually talk about with attention, and it's kind of motivated a lot of like research. So now you've probably seen a lot of these new works nowadays about like different models. So like maybe you've seen things like Mamba, Raku, all these like linear recurrent models, or other like alternative types of attention. So in this work, we consider mainly the idea of like top K attention. So the idea of top K attention is that for every single key I mean, every single query in your sequence, you only look for the top K keys. So you fix the window size technically that you're looking at with a given token. And so this kind of reduces the attention computation actually to be something linear, because if you can imagine your query's size will kind of grow, I guess, with the sequence length. But your key size is going to be completely linear because for every query, you only will look at, let's say, K keys. And so this part becomes, this makes like the computational bottleneck of attention like much smaller. But at the same time, there's some issues with like causal masking. And another problem is that how to conduct the search in a high dimensional space is very like inefficient nowadays, right now. So we need to find like better ways to do it. Okay. So let me continue this. So just to give like a broad overview of what we did in this work. So what we want to do is like to improve this search. And we do this through leveraging this idea in mathematics called like these Z order curves. And the way this happens is that we kind of like or we kind of like consider this like idea of like a trade-off in like dimensionality. I'll kind of go into the details again after, but the main premise that we look at here is that your keys and queries don't actually have to be like very large in dimension. So if you can imagine, if you recall with a lot of these attention models nowadays, you have key and query dimensions maybe in like the hundreds, maybe the thousands, but we kind of see that you actually can reduce these like very, very small values. So things like 4, 8, sometimes maybe 2. And what's really important about keeping this dimensionality is the value, because the value is what captures like the semantic information about each token. And on the other side, like there's some small things that happen because of how we're doing the search that require like changing the softmax. And we do also make a change here that I'll kind of describe later, which is maybe a little bit less intuitive, but it helps significantly with maintaining these like distances when we're really looking for the top K at similar tokens. So to start off with like, the idea of what a Z or a curve is, basically the idea is to take a high dimensional, let's say a vector, so like a dk dimensional vector, into a single dimensional curve on this like 1D space in this type of like bit format. So just like the zeros and ones. And so the way this kind of like works is that it's like it kind of preserves locality. So essentially like nearby points tend to keep the same like distance ordering. So you can imagine that, let's say like I have one of a single token here, and things around it. So let's say this token, this token, this token will kind of have the same distance ordering once you do this projection. Now, this isn't maintained for very far away distances, but when you consider in our use case, which is top K attention, we really only care about like, this like small closest neighbors. Like the K values are usually pretty well, maybe like around like 32, 64 or so. And so usually you're able to keep like the actual like recall on these K tokens pretty consistent. Whereas no, we don't care so much about everything that's like kind of really far away anymore. So we kind of ignore that and we don't really it's like we don't care about how the Z or curve projection actually like influences that part. So what this allows us to do is like basically you have all your keys or queries and you can project them all in parallel onto this like Z order, onto this like 1D line essentially. And so once you do all of this, then you can actually do this like very quick like sorting of your keys and queries. And at the same time, you can like now do a search very quickly in this like 1D space, right? Because in 1D space, your dimension is just basically the abs. I mean, the distance is just like kind of the absolute value between the two, right? Whereas in a top like higher dimensional space, you actually have to like compute the norms, which is can get a little bit expensive. Okay, so this kind of goes over the Z order curves that we use. And so basically, the idea that the Z order curves, how we do it is because if you recall, you can first kind of map the keys and queries again to like these very low dimensional space which are much smaller than the values. And so when you're actually working in this like low dimensional space and you're like applying Z order curve to it, the loss of information is like smaller or like minimized. So this means like the Z order curve actually becomes a little more accurate. So it's like because of our analysis of like using these like low dimensions for your keys and queries, there's like a motivation to actually use these Z order curves. And on the flip side, now there's like a couple of things you have to like consider on the kind of hardware end to like make things like respect, for example, like all of this causal masking and this like binary search for like getting the top K neighbors like in parallel. So if I can give you the next page. So the idea like how this works is that to make things like work kind of nicer on the GPUs. We kind of have to like program our own little like training kernels for this, but basically you can project everything to Z order curves. Then you can like kind of sort them by their distances. So this is what I just described beforehand with the Z order curves. And now when it actually comes like doing this like on your hardware to like make things like work nicely, so we kind of like separate things into like chunks so that it's like you don't actually have any information leakage from the future. So basically the chunks kind of like limit that you're not going to be looking at future tokens when you're computing information from the prior token. So if I'm looking at like the first chunk, for example, it's just tokens like 1, 2, 3, 4, right? Then I can like I can take like the fifth query and I can look at things, right? And then by the next like query, then I look at the next like top K tokens or so. And so there's a little bit more details here. You can look at the paper for the exact algorithm for this, but the idea is just that it's like we have to kind of play around with a lot of things just to make this type of like sorting and searching more efficient on the GPU because it's not naturally supported in most intensive implementations. And so now I think I mentioned that made another change, which was the softmax. So we have to kind of like motivate this a little bit, right? So and like this like dot product like type of setting, there's a little bit of an issue that happens in terms of like you kind of lose information about the magnitude of your token. So if you can recall a little bit about like the dot product, is like it's basically doing like a cosine type of like similarity of like looking at the angle, right? But that's because it gets normalized in the actual softmax. So you're losing this like kind of magnitude information. But in terms like top K attention, like this magnitude actually kind of matters a little bit. So using a direct softmax with it kind of isn't like it usually isn't it doesn't end up being like very effective. So we have to like find a way to change this a little bit. So you can have like let's say like K's and Q's like starting to like produce like slightly misleading types of classifications. So this is like a very simple like idea in like the 1D case. But what we need is like something that can like preserve like Euclidean distance as well as these magnitudes. So how do we do this? So we kind of introduce this like adaptive Cauchy softmax. So what this method does in like if I put it more simplistically is that you kind of just add a couple you can add like a trainable parameter that controls for like how I'm trying to find the right word. How dense or narrow, I guess, the distribution is along for like the softmax. So like how your attention weights are essentially spread out. And this kind of can help like make like allow the distance tokens or such to like maintain distance. Like it takes care of also all these like issues with magnitude that we did because like now you're just doing like these distances here with the dot product like the magnitude. I mean with the norms, let's say. And so this kind of can enhance a little bit like the flexibility, especially like these low dimensional cases. And we see that like it works quite well. So we have like results on one of the more classic original tasks that was trying to measure like transformer efficiency on longer sequences, so LRA, and we could basically kind of beat more or less everything here by like semi-significant margins or something that are actually pretty good. Uh, but like I think nowadays, if you kind of remember a lot of these new architectures that are coming out, these kind of still outperform at tension in general. So like we don't really compare with that. In terms of if we're comparing with like a transformer, we can kind of maintain pretty good perplexity relative to like a vanilla transformer as well, despite being like only a top K attention method. We can also measure, for example, like how efficient or how fast our kernel implementation is. So it's like we can measure in terms of like throughput, which is basically the number of like the speed of being able to like process a get fixed size type of sequence. So you can see here that, for example, we're better than a torch, like a general torch attention. We don't like, and like we're kind of better for like than flash attention as well, but we're not as good as Mamba, which is obviously has like a type of inductive bias which makes it much faster on these kind of settings. And if we kind of consider like throughput as well, like, we're pretty comparable. We're better than torch attention again. Not throughput, but memory consumption here. It's like we're not as good, I guess, as flash attention, but we're not significantly like worse than it, I guess. But again, compared to Mamba, which is like an ideal point with like how the model kind of stores everything. Well, we're not there yet, but this is a promising direction to us to like compare or like to like look at because like at least performance wise. And so to kind of go over what we just did in this work, right? So we introduced like this efficient like top K attention mechanism using, for example, the Z or curve projection to do this fast search of these top K tokens, as well as like adding this like Cauchy softmax modification to the original softmax to maintain positional kind of I mean magnitudes and to like ensure like you're looking at like the right tokens. So we kind of show the if you look at the work, I didn't mention it, but like there's a trade-off analysis that we do that's showing that you can actually reduce this K and Q pretty to like pretty small numbers without like actually significantly reducing performance based on like some error bounds. And performance-wise, because like we're using this top K attention, it's very efficient. And at the same time, we show that it's like it could either matches or like exceeds baselines and multiple benchmarks, or in settings where you don't expect it to do super like maybe as well as terms of is like the dropout is like very minor and maybe insignificant. But there's like again some kind of downsides to how we implement this. So like one thing is like we kind of there's like a lack of positional encoding for like the Euclidean distance measure. So basically, it's like it doesn't like naturally integrate like this positional information. So it was like we had to add like we can't really add like positional information anywhere, and this kind of makes things like maybe worse than like rope-based methods. It might like affect like extrapolation. And right now, it's like everything. It's not a plug-in method, so we kind of had to require like pre-training from scratch. So you can't really use this method to like adapt anything like on the fly. Like you can't just take a llama or like a Pithy or like GPT type of model and just like, automatically change it. So this kind of like highlights, I guess, most of our work. But if you have any like questions or comments, feel free to ask in whatever time, I guess I'm allotted for this.